let's get started. So hello, everyone. Welcome to the fourth season of the SNAPP seminar series. We are very, very happy today to have our first speaker of the season, Gal Mendelson, joining us. And as I explained in the announcement email, this year we're also trying something new, and then we're going to have a discussant. And then the discussant is going to be Michel Mandjes. So let me just very quickly introduce Gal and Michel. So Gal is a postdoc researcher at the Grad School of Business, Stanford University. He got his PhD in electrical engineering from the Technion, Israel in 2020. And he spent a year at NVIDIA before starting his postdoc at Stanford in 2021. His research focuses on resource allocation problems in service systems, decision informing statistical analysis, and the interplay between the two. Michel, I think, is quite well known in the community as well. Michel received his MS degree in math and econometrics from the Free University in Amsterdam, the Netherlands, in 1993, and then received a PhD in operations research from the same university in 1996. He's currently a full professor of applied probability at the University of Amsterdam, and is also affiliated as an advisor with Eurodom Eindhoven, the Netherlands. He was visiting professor at Stanford University and Columbia University, and he's currently project leader and main applicant of the large Dutch consortium grant networks. His main research interests are in stochastic processes, queuing processes, efficient simulation techniques, and application in transportation and communication networks. The way that the seminar is going to work today is, and I apologize for taking the time, that we'll have about 40 to 45 minutes of the regular presentation, and then leave about 15 minutes for Michel's discussion. If you have clarifying questions, please feel free to shout outs during the presentation. But if you have longer questions, please leave till the end. And also, please, if you have questions, feel free to put it in the chat box. Now, without further ado, let me welcome Gal, and then later Michel. And then Gal today is going to talk about detecting persistent service rate slowdown in service systems. Yeah, Gal, please.
Thank you, Yuan. Let me share my slides so everyone can see. Can you see the slides? Thumbs up. Okay, great. Again, thank you, Yuan, and thank you, organizers, for inviting me to give this talk. I'm very excited to kick off this seminar series. So I am going to talk about the interplay between control and statistical analysis in service systems, and specifically for the task of detecting service rate slowdown. And this is joint work with Professor Kuang Xu. So just a little bit of background. One of the main goals of service systems is to balance supply with demand. If the demand exceeds the supply, either in the short term or the long term, then you get congestions, for example, queue lengths build up, and you get degradation of quality of service. And if the demand is less than the supply, then essentially you're underutilizing your resources and maybe wasting them. So balancing between these two is one of the main aspects that in service systems. So here are some key considerations for decision makers in this type of systems. One is, how many servers do I need? How many beds in the hospital ward? How many telephone call center employees, or how many servers do I need in my data center? The second thing is, which we sometimes take for granted, is the service capacity of each server. So it doesn't only matter how many servers I have, it also matters what is the service capacity that each service can provide for the supply in the system. And especially in large scale systems, but in many systems, it's pretty frequent that there are changes to service rate of servers. And this is something we need to expect, and this is something we need to deal with, because we want servers to work at their full capacity to match demand with supply. So slowdown detection of service rate, not just a 0, 1, something failed or not, but maybe in a continuum of slow down by 40% or something like that due to any reason. We want to detect that quickly. And the third aspect of decision makers have to take into account is control, resource allocation decisions. In our context, it will be load balancing decisions. Jobs come, who's going to serve them? In this case, it will be routing. So this talk is about the interplay between control and service slowdown detection. So there are a few perspectives on which this type of problem has been looked at in the past. Essentially, anomaly, fault, change point detection, all of these kind of point to the same thing. Everything is fine, and then an event occurs, and this changes something in an unwanted way in the system, and we want to detect it quickly. But this is a very large body of literature, each of these terms separately and combined. And while there may be overlap, there's also very distinct flavors on how you would look at anomaly detection problems versus fault detection, etc. I hope we will have time by the end of this talk to kind of talk about how our work fits in the context of these kind of terms, but I think the closest thing is probably change point detection, but you will see a big difference once I lay out how we look at this problem. So our goal is to quickly identify the persistent slowdown and server rate of server. This is a dynamic problem. We get data in an online fashion, and we want to gather statistics, perform some tests, and maybe get notifications if a server slowed down. And we want to know the following things. One, that a server slowed down. Two, which server it is. So there's an element of identification here, which will be important, and I will talk about this. And also some indication on by how much did it slow down? Is it 2% or 90%? Like I don't mind if you don't tell me that the server did not slow down by 2%, but I do want you to tell me if it slowed down by 90%. So this will drive kind of our engineering thinking about this problem. Okay, so here's the model that we will have throughout. It's the usual well-known parallel server model. We have K servers, which is fixed number of servers. Each server has a service rate constant, by mu I. Jobs arrive to the system, for example, as a sound process, and they arrive to the load balancer, which must implement some control mechanism, in this case, a load balancing algorithm or routing, to immediately send each incoming job to one of these servers for processing. And we denote the load in the system by rho, which is just the ratio between the input rate, lambda, to the sum of the service rates. All right, key assumption throughout this talk. We assume that before slowdown, when everything was fine, all of the servers have the exact same rate. We don't deal with the case where before slowdown, the servers may have different rates. Also, another assumption is that we assume that if a server slowdown is just one, we don't talk about what happens when multiple servers fail at the same time, although that's a very interesting problem. And the way we think about slowdown is we introduce a speed factor alpha, which is a number between 0 and 1. And if server I slowed down, then its service rate changed from mu to alpha mu, as you see in the red here in the picture. So looking at the timeline, the red line here indicates an event at which server I, so alpha here is 0.3. That means that server I slowed down by 70%. And the green line here, hopefully the green and the red will be very close together, is the detection. And we hope to get some notification on the fact that server I slowed down by 70% by the green time. The way we look at this is by using window-based detection. So the point is that we're going to divide the time axis into consecutive time windows, and we're going to gather data in each of these windows, do statistics, test, and per window decide whether we declare that something went wrong. Okay, so in this case, you would see at the end of window 3, this notification, service I slowed down by 70%. This will be great. Now, of course, you can optimize this. You can do a sliding window, maybe. You can do look at testing for multiple windows at the same time. You can even do sequential hypothesis testing. But we stick to this very, very simple framework because it allows us to flush out some interesting insights about the interplay between control and statistical analysis. All right. So what is the statistical framework here? Within this window-based detection scheme, we want to decide what data to collect. For example, let's sample queue lengths, the different servers. We want to decide what is the summary statistics we're going to use, for example, average. What is the test? For example, comparing averages, maybe to one another and maybe to a threshold. And finally, guarantees that we have on failure or success probabilities. Now, importantly, for the rest of the talk, at least the theoretical part to make sense, when we think about collecting data, we are in the analysis, we think about sampling independently from steady state distributions. Now, clearly, this is not really the case when you apply a time window in an online fashion in a queuing system. But because it's really hard to analyze the transient behavior of these types of window-based schemes in queuing networks, we use this as a method that serves as an approximation of what would happen if you actually use this data, the actual data. And I will show you simulation results which kind of concurs with the fact that this is it's a good way to look at this problem. All right. Okay, so let's talk about detection and why would it be hard in this type of system? Why is it challenging? So the first key thing is understanding that interaction plays a key role. When I say interaction, I mean dependence between the queues. So let's start by thinking about what does it mean that we don't have interaction and what do we do then? So if we had these several servers, each one independently has its demand from has a demand that's independent from the other servers, and these these queues are simply unrelated to one another. Then we will just collect data separately. We would use separate statistics, and we would test separately, and this might work well. An example in our setting, sorry, where this occurs is where the control is random routing. So if we take the control to be random routing, meaning that every jump that comes, we just choose a server uniformly at random, then essentially we are decoupling the queues and we have k independent MM1 queues, and their distribution only depends on the load here, meaning the ratio between the input and the out and the service rate. Now, since the input remains the same no matter what here, if a server slows down, we will probably see an increase in that queue length compared to other queues, and that might facilitate detection. So this is what happens when you don't have interaction. But what happens if you do have interaction? There is some dependence between the queues, and the first thing is to try to understand what causes interaction. And the answer is, in this system at least, adaptive control. When I say adaptive control, I mean a load balancing decision that's based on the actual state of the queues. For example, join the shortest queue, of power of choice. All of those state-dependent load balancing decisions actually couple between the queues. And it's not really clear what we do then, because essentially the adaptive control tries to balance the queues. So we might not see this difference. We might see the difference in the overall traffic in the system, but we might not be able to identify which servers slow down because of the adaptive control. Now, on a high level note here, this type of thinking about inference and experimentation in the presence of interaction between units, especially in large scale system, this is something that's currently a very active area of research, but as far as we know, not on interaction caused by control in queuing systems or interaction or for the specific task that we're talking about, which is detecting service rate slowdown. All right, so here are the main takeaways from this talk before I dive into them. First is that adaptive control may render congestion data to be ineffective for statistics. Okay, and there are nuances here, and I'll discuss them shortly. Decision data can be a very powerful statistic. And when I say decision data, I mean, instead of looking at the state of the system and collect that data, such as QLAMs, look at the decision the load balancer makes instead. And the reasoning here is very simple. If we have adaptive control, which tries to mask the difference in the state of the queues, that means that if an event happens, such as service rate slowdown, the control had to adapt to it, meaning the distribution of the decision that it made would change due to the service rate slowdown. So look at the decision data, not the state data. Another very powerful feature is the fact that the decision data is a very simple data. It's just 1 to k, and it will have a categorical distribution, and we take samples, it will be a multinomial distribution, and this is something we can work with, as opposed to QLens, where we don't even know the stationary distribution under JSQ for 2 servers. Okay, so we don't even know how to start planning a test there. Third thing is not just the decision that it can be powerful, but also let's think about how to actually use it. Okay, and there are a few challenges there. I will touch upon this based on the time that I have. And finally, small changes to control can lead to large statistical benefits. Now, this is something we're not so, at least I am not so used to thinking about, which is, for example, the tie-breaking rule in load balancing. Because usually the analysis that we do on performance, different controls, the tie-breaking rule doesn't really matter. But here, because we are actually isolating the decision data and try to use it for statistics, it really matters how you break ties, because there are ties all the time in these types of systems. Okay, and I will demonstrate what I mean by this. So this is a surprising and interesting kind of thing here. Okay, before I begin, a word on measuring service times. So if our goal is to identify persistent slowdown of a server, then the immediate suspect will be just measure service times of jobs in each server, maybe average, maybe look if that average changed, and just infer the service rates and say that something occurred. And this will work well. But this information is not always available. It could be for many different reasons. 2 examples of this is, one, let's say that the company that has this infrastructure for the load balancer and the servers that provides this service, for example, Amazon AWS, and there's another company running its applications on that infrastructure, then for privacy reasons, Amazon doesn't have access to the application level data, such as how much time it takes to process jobs of that company, right? So there are privacy issues. The second thing is that even if you own the entire network and everything's yours, still, if you don't have this information pipeline, this information channel of getting measurements of service times up towards wherever you're doing the statistical analysis, for example, at the edge or at the load balancer, then introducing such an information channel means designing, implementing, testing, deploying, it's costly. So it makes sense to ask the question, can we use data that's already available to the load balancer, for example? And this is where QLens versus decision data comes in perfectly. All right, let's start. Here's a toy example, and we're going to use this to get some insights on the interplay between control and analysis and statistical analysis. Let's think of a magic load balancer, which actually knows the service rates. Before the slowdown, after the slowdown, it always knows the service rates. Okay, and this is a toy example because that's our goal. But let's say it knows the service rates for this thought experiments. And the load balancer does what's called random proportional routing or rate adaptive, which means that for every time a job arrives, it just randomly routes it to one of the servers but with a probability that's proportional to its service rate. Okay? So what will happen here if we try to use the queue length data for inference? Essentially, what happens here is that all of these queues now are independent, identically distributed MM1 queues, because they're independent because of the random decision here, and they're the same distribution because it only depends on the load, and the load is actually the same on all servers. So we might see an increase in overall queue lengths in the system when a server slows down, but we will not be able to identify which one it is because the distribution of all queues is identical, exactly, and independent. Okay, just impossible. So what does this tell us? This is already an example of the first takeaway. Adaptive control, and this is an adaptive control because it adapts to the actual service rate, may cause congestion data, such as queue length, to be ineffective for statistics. In this case, completely ineffective. Somehow, the adaptive control completely erased the information from the state, which makes sense in some way because adaptivity tries to kind of mask changes. That's the whole point of adaptivity. But where did that information go? It went to decision data because the decision frequency for each server changed now corresponding to the change of the service rate change. Okay, so this also already gives us a template of what we are looking for in terms of the interplay between control and statistical analysis. But to be fair, there are questions here. First of all, is this a general phenomenon, meaning outside of this toy example? Second question is whether or not there is a trade-off between control and detection. Should I give up optimizing for performance in my adaptive control to make detection better, or vice versa? So the answer to the first question is yes, this is a general phenomenon, and we'll show you that it is. And the answer to the second question is yes and no. This is a more complicated answer, and I hope we get a chance to talk about this at the end. And let's start with trying to figure out whether this is a general phenomenon by analyzing a different adaptive control, which is not a toy example, and it's join the shortest queue. So whenever a job arrives, the job is routed to the server with the shortest queue at that time. And we are to take even a simpler setting where we know that one server slowed down. We know that one server has a rate of alpha mu instead of mu, but we don't know which. And we are going to analyze this in moderate to heavy traffic. And the reasoning is we have two reasons for this. First, when is it most important to detect the service rate slowdown? It's when the system is more loaded, because you need that capacity to serve that system. Second thing is that if the load is very low and you don't have many jobs in the systems, you don't have data to begin with to do any inference anyway. So analyzing these systems in moderate to heavy traffic makes a lot of sense to get insights on what we want. So how we do this? We do this by a well-known technique, by looking at a sequence of systems indexed by M, small m will go to infinity. We're looking at steady state, systems in steady state. The service rates are fixed, but the arrival rate is scaled with M such that it increases to the maximum capacity of the servers, which is the sum of mu j. And the load here would be rho M, depends on M, and will increase to 1 from below. All right, well-known result is state space collapse, which means that if we look at the vector of the scaled queue lengths in steady state, this converges with M in distribution to a random vector with identical elements. In this case, each of which has an exponential distribution, but we're not going to use that. We're just going to use the fact that the convergence is to the same random variable, either marginally or as a vector. And the question is, are we done? Because this result tells you that in heavy traffic, and even before that, I think, the queue lengths are essentially indistinguishable in this setting. So would that mean that you cannot do statistics? Interestingly, the answer is no. We're not done. And this was very surprising to us, but it turns out that performance and what we use for performance analysis, for example, statistical collapse here, is different from how we would think about statistical analysis in these types of systems. And I will flush out exactly what I mean now. All right. First thing that matters is, all right, we decided to collect Q-length data, but the question is, when do we collect it? And turns out this is very important. Whether or not you're collecting data in a synchronized fashion or asynchronized fashion. What you see here is an example of a synchronized fashion. These are the rows are the servers 1, 2, and 3, and this axis is the timeline. And here we're collecting Q-length information at the same time. We just sample the joint distribution at different times. This is what we call synchronized. The other option is just randomly a sample from the marginal distribution of Qs. For example, if you have Q-length information arriving to you because you have, I don't know, an adaptive control with sparse communication protocol, whatever caused, maybe it's by design, whatever caused you to take like sparse measurements of Qs, this is another option. So essentially, we're sampling from the marginal distributions, and we're treating all these samples independent. The second thing that matters, besides when, is what do you do with that data? What is the statistic that you use as a summary statistic? You can either do marginal statistic. So in this example, let's see the blue row here above. We take measurements in a synchronized fashion, but our summary statistic is by looking per server, like the average Q length of these samples of server number 1, the average Q length of server number 2, etc. And that will be an input to the test. This is one way of doing this. The other way of doing this is doing joint statistics. Instead of doing this summarizing across like per server across time, we can summarize for each time across servers, and that will be an input to the test. Now, I'll already give a promo here. The second thing here with a joint statistic will be the strongest option in the presence of adaptive control. And the way we're going to do this is by looking at decision data. And how is this related to decision data? Because we're just looking at Q lengths here. It's because the decision data that we're looking at is defined as look at the state of the system. If a job is routed now to the system, where would it go? So if we summarize the statistics, if we summarize the statistics per sample, we can look at who's the minimal Q length at that time, right? That's exactly the decision data. Okay, I don't have time to go more into this, but just keep in mind, joint statistic plus synchronized is decision data in this case. All right, we have 3 options, asynchronized plus marginal, synchronized plus marginal, and synchronized plus joint, which I just told you is, in this case, decision data as an example. And fourth option doesn't really make sense because doing asynchronized and joint doesn't, what's the meaning of sampling for a specific time? And there's no meaning to that, okay? So these are the 3 options. And here's an informal summary of our results, and I will dive deeper into the rigorous derivation and statement of these shortly. But to get a picture, for high enough loads, reasonable tests fail if you do marginal statistics. For example, if you just look at the average of Q1 versus the average of Q2 versus the average of Q3, etc., doesn't matter how you sample versus synchronized or asynchronized, reasonable tests will fail. We will define what reasonable means in a minute, but that's kind of the general picture. And as I said, sync plus joint, there exists a good test, which will be the topic of the end of this talk, which is decision data. So now I'm going to focus on the 2 thumbs down, the negative results, and try to explain them in more detail. So in this case, where we start with asynchronized plus marginal, meaning we take sparse samples and we summarize per server, then we have a matrix of Q-length samples all of them are independent, and each row are IID random variables because we sample the same Q length for each row. And let's define what a reasonable test mean in our setting. So because we are summarizing over each row, let's define a function, which we call G, which maps a row to some non-negative number. This will be the summary statistic. Think of average, for example. We're going to assume two things about this G. One is that it's continuous, and the second is that it's scale invariant. So examples of functions that adhere to these conditions are the arithmetic mean, the geometric mean, the harmonic mean, all of the p-norms, the maximum, essentially every reasonable usual thing that you would do to summarize data adheres to this. So this is pretty general for what we want to do as a summary statistic. And we denote the ith row by xi in this matrix. So G of xi is the marginal statistic for qi. Again, think average of samples. And we are going to do hypothesis testing, where the ith hypothesis, hi, is that server I slowed down. What is the test? Fix some number, delta, positive number, and we would declare that I slowed down if G applied to the data belonging to xi is substantially different from the rest of the G's. So if you think of averages, we would declare that the ith server slowed down if the average of qi is by some factor of 1 plus delta, which can be as small as you want. The delta is separated from the rest of the averages. That will give us good indication that server I did indeed slow down. And else, if we don't know, we say inconclusive. Now, of course, you can optimize this. What if there's a tie? What if okay, but we are trying to make this very simple. Just inconclusive, we don't know. Here's our result. For any gamma larger than 0, this can be as small as you want, there exists an M0, which is dependent on n, the number of samples you took, delta, which was in the test, and gamma that we just fixed, such that for every m larger than this M0, we have on the left the probability of success is smaller or equal on the right to 1 over k plus gamma. Now, I'll remind you that as m increases, the load increases, and these x's are scaled with m, okay? So I just didn't put that superscript there just for notation reasons, but for simplicity, but everything here scales with m. So saying that there exists an M0 such that this happens means that for high enough load, the probability of success is arbitrarily close to 1 over k. Now, 1 over k is like saying, well, let's choose a server at random without looking at the data, and that would perform the same, right? So this is not good. Essentially, this means that we don't have identification of who or which server actually slowed down. Here's a short proof outline, but how we do this. We take the event in this probability here in the middle, and we multiply by the scaling factor, and we use the scale invariance. That's why it's important here to get that 1 over square root of m inside the G. So, and the X is comprised of Qs. So the scaling factor would go to those Qs, and then we could use state space collapse result. In this case, we would use the fact that each of these independently converges in distribution to the same distribution. We're not going to use the fact that they collapse at the same time, I mean, because this is asynchronized. And we use the continuous mapping theorem and just a simple symmetry argument to get our result. Next, negative result is synchronized plus marginal. So we are taking the interaction of the Qs into account by sampling from the joint distribution at different times, but we insist on doing marginal statistics per server, okay? This is even worse, turns out. And this is due to the actual collapse of the joint statistic of the steady state distribution. And how we prove this is, again, introducing the scaling factor inside and just rewriting the event in the probability here in the middle by just taking this one here on the left and moving it to the left-hand side. And if you look at the probability on the right, by the end here, what we see is that on the left-hand side, because of the state space collapse, and remember, xi's are rows, but we took samples synchronized. So these vectors actually, in the limit, have the same distribution when they're scaled. So the left-hand side converges to 0 in probability, while the right-hand side here converges to a non-trivial, non-negative random variable. So this probability, as m increases, will be as small as you'd like. All right. So intermediate discussion. We've seen that looking at marginal statistics, summarizing over each server separately, and doing asynchronized sampling is not really the way in the presence of adaptive control. At least we think the evidence suggests that. We should probably think synchronized plus joint, but how? And I already gave away the answer, decision data. And rate adaptive example, the toy example that we have, pointed towards decision data, does JSQ as well? This is a question I want to answer now. It does. And instead of showing more math, let's just look at how it looks like. Okay, so here I'm showing you a simulation of JSQ in 95% load. What we see here is consecutive time windows, windows 0, 1, 2, 3, etc. And for every window here, the y-axis is the normalized Q length over averaged over all of the window, and the x-axis is the servers. We have 30 here. So a point in this graph, in each of these graphs, it means this server over this window had an average Q length of whatever the number says, and it's normalized over the entire picture. So this picture, I need to make my decision whether or not a server slowed down during this simulation, and who, and maybe by how much. And I'm not really comfortable with looking at this picture and making such a statement. It looks really noisy. I might be able to force some idea, but this doesn't look good, okay? As opposed to action data or decision data. So this is the same simulation, but we just used the decision data to display here. And I think you can agree that it's clear that the middle server, server number 15 here in the simulation, in window number 4, slowed down. And we can even think about by how much it slowed down by looking at the difference between the action frequency, which is what's displayed here on each graph of the other servers compared to this server here, because it's substantially decreased. Okay, so this gives us a very good intuition, and that decision data is very powerful. All right, so let's talk about decision data. What is it and how to use it? So let D be the decision random variable, and this is defined rigorously as follows. We think about, I did not provide the technical details here in the assumptions, but we think about our parallel server model with, for example, Q length based adaptive control, such as JSQ or whatever it is. And there's an underlying Markov chain, which is irreducible and positive recurrent whenever the system is subcritical. And we define this random variable to be sample the Q lengths or additional data that you need for your Markov chain, sample this Markov chain in steady state. If a job arrived, where will it be routed to based on that sample? That's the definition of the decision random variable. Clearly, it can be the numbers 1 to k, and we denote pi, the probability that this decision random variable equals to I. So this has a categorical distribution, and if we take n samples, a multinomial distribution, which is very nice to work with. Another key advantage of looking at decision data when possible. So a conclusion from this simple definitions is that, from these simple definitions, is that we expect detection to be possible based on decision data if the probability of sending to a slow server is substantially separated from the probability of sending to a non-slow down server. In this case, it will be the difference between all of the dots that go together and the dot on the bottom when you see windows where servers slow down. So we need to think about whether or not these probabilities are separated for adaptive control. And good news is that we have a general separation result saying that for any adaptive control that's throughput optimal, not just JSQ, not just rate adaptive, we have a bound, an upper bound on this ratio, which goes to the maximum possible as rho goes to 1, which is alpha, which is exactly the speed factor of how the service rate changed. And but even for lower loads, you get numbers that are really close to the actual alpha. So here is an example where we have 30 servers, one server slowed down by 40%, meaning alpha equals 0.6. The load is 0.85. It's not 0.99999. And this ratio is bounded from above by 0.7084. So there is a clear possibility of detection here if we take enough samples from these multinomial distributions. All right. Okay. So now let's talk about a little bit about how to actually use decision data. From the little time I have, I will give you kind of the basic recipe that we think of. More information on this, I will also give a talk at the upcoming Informs annual meeting, and I will emphasize more this part that I don't have a lot of time to talk about here. So if you're interested, you're welcome to join. Okay, decision data samples are D1 to Dn. We are going to start very simple. Let's assume we're in a world where we know that if a server slows down, its rate is alpha mu, a specific alpha. Okay, of course, in reality, we want a continuum of possible slowdowns, but let's start here. And it turns out we can go very far with this. All right, so this is discrete hypothesis testing. And we're just going to use maximum likelihood with the error defined as usual, okay, for maximum likelihood tests. And first result here, it turns out that this maximum likelihood test is equivalent to a simple threshold test using the empirical distribution of the decision data. Meaning, just look at the frequency of how many jobs are routed to each server. Take the one that's the minimum. That's probably the one who failed or slowed down. But in order to balance the error versus the possibility that no server slowed down, you also want it to be below some threshold. And this is what you get. So essentially, it's very, very easy to implement because of this equivalence and this result. All right. We have a few challenges, and I know I have about 5 minutes or even less, Yuan. So I'll try to make this brief. We plan the test for a specific alpha. This is probably not good enough for applications because we don't just want to find out if a server slowed down by 40%. We also want to know by 90%, right? The second problem is that we have seen that P slow divided by P not slow is key for detection, but it's not exactly the alpha that we planned for. So the bound doesn't tell us exactly, but it's not exactly the same quantity. It's maybe close for high loads, but it's not the same. And the third issue here is how do you choose the window size? How do you choose the number of samples and guarantee small error probabilities? Because I don't have a lot of time, the last two items, I have the answers that we advocate for, at least in this setting here, and we can certainly discuss this afterwards. I'll be very happy to. But I want to focus on the first one, is how do we plan for a continuum of possible slowdowns and not just a specific one? So here's the answer of how we plan to do this. How do we suggest to do this? Essentially, this is a composite hypothesis test. We look at the continuum between 0 and 1 on what the possible speed factor can be, which means what the slowdown is. And essentially, we divide this continuum into 3 areas. One, on the left, this is an area where if the actual slowdown was in this area, I want to detect it with high probability, no matter what. And I want to get the right server. when I say which server slowed down. The right area between this beta, which I'll discuss in a minute, and 1 is an area which says here, just say no slowdown. I don't want to detect anything here. It doesn't really matter. 10%, I don't care. I care 40% or more, okay? Because you have to balance the error probabilities of these tests. And if you don't do this, you will just get a bad error. And finally, and this is our solution for the problem of the composite hypothesis testing here, is to introduce a buffer, which means defining a beta that's larger than alpha. And we are going to change the definition of the error of the test, of the usual error, to something else. We are going to demand that in this error between alpha and beta, just don't declare the wrong server. You're perfectly fine with saying no server slowdown, and you're perfectly fine by saying the right server slowdown, even if it's was between 20 and 40, and it's actually was in the 50. You're fine, but just don't say the wrong server. So this is a different definition of an error, and that's what allows us to do the following step, which is this complicated composite hypothesis test is actually equivalent to a discrete hypothesis test using alpha, beta, and beta. So this is a result we have. So we can now take this continuum and just forget about this continuum and go back to discrete hypothesis testing. And the proof is interesting, which I don't have time to kind of go into, based on coupling arguments, based on multinomial distributions. Again, because the decision data is so perfectly distributed as multinomial, we can go a long way of getting these kinds of results. So to conclude this part, and just a quick word after, the discrete hypothesis test that is equivalent to the composite hypothesis test is just incorporating these, that's incorporating these HI betas into the possible hypothesis that we test for. And lastly, proposition, this discrete hypothesis testing is again equivalent to a simple threshold test. So we finished the entire picture, at least with the challenge of detecting a service rate slowdown using decision data on a continuum. Because now we can say, look, there's a simple threshold test, and this is proven. Finally, quick word on the tie-breaking rule. We usually assume that the tie-breaking rule is either done randomly or by index, for example. Doing tie-breaking rule randomly, and because there are a lot of ties all the time, introduces noise to the decision data. And this is how the picture looks like on the left. And if you do by index, it introduces bias because you prefer servers over others whenever you're breaking ties. And this is the picture. You can see the slowdown of the server, but there's a substantial bias in the data. So what we do is we introduce a new tie-breaking rule we call adaptive round robin, which I think you can agree with me, denoises and debiases the action data in a very profound way. All right. So these were my main takeaways from the talk. Adaptive control may lead to congestion data being ineffective. Decision data can be very powerful. A quick word on how to use decision data with our discrete hypothesis testing, which is equivalent to a threshold test, and tie-breaking rule as a way to optimize the actual data that you're using for detection. Thank you very much. Was very happy to give this talk.
Thank you, Gal. Thank you, Gal, for a very interesting and thought-provoking talk. Let's quickly move on to the discussion, and Michel is going to provide some of his perspectives.
Well, thanks a lot, Gal, for this wonderful talk. I enjoyed it very much. Of course, I read the paper already, but it was very helpful to see well, your explanation once more. Before going into it, I want to start with a short announcement regarding an online workshop to be held next week. I think the announcement was already distributed through the SNAPP email list. I think it's a wonderful workshop like the previous time. Very strong speakers, really, well, the topic that you are working on. So I hope to see you all next week. Yeah, so let's start my comments on Gal's story with my let's say, general view on the area in terms of the relation between OR and data. Well, stochastic operations research, I guess, is the area that we're in, and that works with complex systems that operate under randomness and uncertainty, aiming to develop mathematical models and techniques for the analysis and optimization. So I think that is basically what all of us are working on. And, well, you know, the application areas, transport, logistics, healthcare, maintenance. And the question is, well, how do you solve those problems? And there is like this conventional approach that works as follows. So there is like a model that you estimate in some external loop. So you try to estimate the parameters of your model. There is some model selection going on. Then given that model, you try to evaluate the performance of the system. So that could be a queue or an inventory system or so. And typically you do that using probabilistic techniques, queuing theory, for instance. And then after that, you can design your system in order to optimize the performance of that system. So that could be in terms of like a control mechanism or so. I think it's a legitimate question to ask yourself, well, is this really the way we should do it in 2022? And just a few considerations from my side. First one being that, well, in the approach that I just sketched, there is something like a model and a parameter, or multiple parameters, of course. And I think it's necessary to also bring the uncertainty of those parameter values into the equation. So there is a need for online estimation. And in addition, you want to detect, well, failures that could happen along the way. And a second thing that is, I guess, important to include is that, well, basically the schedule changes the system. So the doctor works faster when being behind of schedule and slower when being ahead of schedule. In general, I think we typically use time homogeneity properties that are not always justified. And a question that comes up is, should we simultaneously estimate and optimize / control? And that is, of course, at the very heart of Gel's presentation. These themes are really topics for the special instance of his model that he has been reflecting on. Well, if you want to know more about my general view of this area, I thought about it quite a bit over the past years. Have a look at, well, the recorded talks of last year's DDQC. So I gave a tutorial on it, and, well, there I sort of sketch my view on the area. So let us focus on what Gel has been doing. Well, the interesting feature is really that he looks at the interplay between fault detection and estimation. So that is really a subtle point that's, well, I'm not sure whether it was overlooked in the past, but it didn't get much attention. So there is this controlled queuing system that is, well, that is working, and you want to estimate or detect things in the context of a controlled system, and that is typically hard. So Gel explained why that is. So the control action quite often counteracts the estimation opportunities. So very briefly, what I feel are the main conclusions of Gel's work. In the first place, I think it's a very important conclusion that, well, the control loop makes the estimation problem hard, in particular, the identification task. So you could perhaps find out that one of the queues is slowing down, but really the queue that is slowing down, to detect which one it is, well, that is harder. And the other, well, more detailed conclusion, I guess, is that in that situation, it makes really sense to work with action data rather than congestion data. So don't look at the queues, but look at action data, and that somehow makes sense, I think. And to me, the most surprising thing was actually that if you include the tie-breaking rule in control, then you can potentially boost the system's performance quite a bit. So that is really, well, a more technical conclusion, but a very worthwhile one. So I already discussed a bit with Gail a few weeks ago, and well, there were a few themes that came up. So one of the things that I raised, and I think Gail mentioned it already during his talk, that there is this, well, perhaps there is a trade-off between estimation and identifiability somehow, or detectability, if you wish. It seems that in this story, there are two like conflicting objectives. So there is like a controlled system. So apparently one objective is to control the system, but the other objective is to, well, to estimate or to detect. And well, apparently that combination is tricky. One of the things that you could wonder, so that was my suggestion to Gal, was to give up some optimality. So do your control in a slightly non-optimal way, which could potentially make the estimation problem much easier. That would be the hope. In general, I suppose there would be like a control estimation trade-off curve or so. And yeah, I think it would be cool to get a handle on that. And then it's up to the, well, the person sort of steering this system to decide which point he or she wants to be at in terms of, well, control and estimation. The second thing that we could discuss is a bit more of a methodological nature. So detection is, of course, one of the more classical statistical problems. So there is a lot of stuff known about, well, detection of change points in the context of like a random walk. So there is this framework of David Sigmund from the 1970s and 80s, but that is really for uncontrolled systems. So there is like a random walk and you want to know whether something changed in the random walk. But the interesting thing here is that what you observe is a controlled sequence of numbers. And my question to Gail here is there any hope to come up with like a more formal general toolkit for change point detection in a controlled environment? So, well, I guess Gail can choose which question he wants to start with, and we can discuss a little bit more, and perhaps also some people from the audience.
All right, thank you, Michel. So let's start with the first one.
Yeah.
So based on your a talk that we had a few weeks ago, I've included a short word of this in the presentation, saying maybe there's a trade-off between control, because it was the right place to point out this question, I think, and I'm grateful that you pointed it out. And there I wrote yes and no, and there is a trade-off if you insist of doing things in a certain way. If you insist on gathering marginal statistics per server, then we kind of shown that there will be a trade-off. You will be better off for detection using random routing than JSQ, and clearly you will be better off in performance using JSQ than random, right? And if you do something in between, as you resorted to, some kind of a trade-off, maybe power of choice or I don't know what, then you will get some sort of trade-off in that aspect. I also answered that there is no trade-off because we have shown that if there is a way, at least in this specific context, in this model with JSQ or either adaptive load balancing policies, there is a way to do joint statistics, joint statistics with synchronized samples, and you're actually benefiting from both worlds simultaneously. You're doing excellent detection using decision data while having the best performance. So this is why the answer is also no. There is no trade-off.
Isn't then the question also what kind of data you have access to? If you have access to action data, then the answer is obviously no, because that is what you showed. But if you only have access to congestion data, I think then this issue becomes relevant, right?
Yeah, and then there's a trade-off. Exactly.
Answer, I think. Yeah.
Yeah, I think you're right. I think that's the answer, at least of what the evidence here suggests.
Yeah.
For the second discussion point regarding change point detection, so this is very similar in flavor, right? We want to detect if like a collection of samples at some point changed, the underlying distribution changed, okay? And I think that something we were really struggling with, even starting to think about these problems, especially we're looking at Q length, is that we don't know the distribution. And a lot of times you do know the distribution, then you can design tests and stuff like that, but we don't know, right? I said, even for JSQ with 2 servers, we don't know the station distribution. So let alone other models. So it's very challenging to think about how to even start designing these types of tests. But I would say that there is hope for using these mechanisms and techniques in this context, even by just looking at decision data, and instead of doing a window-based detection, which is the simplest thing you can think of, probably not the best, okay, do a sequential hypothesis testing, such as many of the algorithms and change point detection, you would probably get a much faster detection using those same algorithms, maybe enhanced to take into account other stuff, but I think that they could certainly be very effective.
Yeah, my hunch was if you know the exact rule of your control, then in principle you can sort of reverse engineer what, well, not what the input was, but whether it's sort of unusual or not. But that was really like a sort of intuitive thought. Is that also what you were thinking of?
I was more thinking about, look at the classical example of change point detection. You assume you have x1, x2, x3 sequentially given to you. Each of them is multinomial distribution with some distribution. At one point, you start getting x's which are from a different multinomial distribution, and you need to decide when that happened, or very close to when that happened. So that's the way I was thinking about this in terms of using decision data. I don't know what to do about Q lengths. That's a completely different story.
Yeah, well, thank you very much. I think it's pretty much in line with my thoughts. So yeah, thanks very much.
Thanks.
All right. I guess in the interest of time, let's thank the speaker as well as the discussant. Thanks, Michel, for bringing in maybe different and then maybe somewhat broader perspective on Gail's work. And I think we'll stick around for a few minutes if anyone would like to have some follow-up questions. And if not, thank you all for being here. Thank you.